Didn't say.
They must be doing something with the power. No.
See, the thing is, that we have glass in, but it's fucking like the room right next to the, like, gaming stuff, so like, community class, we have an exam.
We should not have.
I got
I have no
Like,
idea.
this guy over here. You know, like-
I have no
See,
idea.
I would try something like classes and there's locations, like, you know, you think they would.
Maybe they didn't realize there were classes after 4:30. I have no idea.
That's like insane, because there's so many at that time.
No idea.
Yeah, it's news to me as of this morning. Okay, let's get started. New module today. Let's think about something other than a particle in a box. We'll certainly use our insights from the last few weeks over the next couple. So I said that the rules that we've learned are in some sense universal. We're just changing the problem we're looking at. But the analysis will be very similar. Of course, we'll get very different results for this system. Let's just kind of recap what we learned about the particle in the box and then just kind of keep our mind in this space as we explore our next application. So our recap. All right, so for the particle in the box, what did we observe? One, the first thing is that we saw that when we talk about, we put this particle inside the box and we ask, hey, where are you when you're at fixed energy? We saw that the system is just delocalized like a wave through the system, right? So in position space, we derived states of constant energy, which are the wave functions, psi n of x. And these are wave-like, right? They don't have the behavior that we would expect for, say, a billiard ball bouncing randomly between two walls or an ideal gas. And I'll remind you what I mean by that. And we looked at, again, just very simply, if we look at n equals 2, first excited state of our system, right above the ground state, psi 2 of x, so square root of 2 over L sine n pi, 2 pi x over L. And remember, what we actually observe is not the wave function, because again, this is a function that goes negative and positive. What we observe is the square of the function, which is our probability. So the probability that particle is at point X is equal to the absolute value of the wave function squared. And then we draw that in our box between 0 and L. Right, our wave function looks like a wave with one period. Right, and this again is very different from what we would expect for a normal billiard ball bouncing with some energy between the walls. Right, classically, if we were to ask the same question for a classical billiard ball bouncing between our walls at some kinetic energy, the billiard ball would have a flat top distribution because for a billiard ball, for something moving randomly in a box, just a normal particle, there's no bias where it is, right? It can be anywhere, right? That's the whole point of an ideal gas. Ideal gas says that inside your box, the pressure is the same everywhere, right? And what does that mean to be pressure? That means the number of particles per unit volume is fixed, right? So in a box with many classical particles, you have classical billiard balls that are just bouncing around randomly. You expect to find the same amount of billiard balls in every little point in the box. So there's an equal probability of finding one billiard ball anywhere. Right, so you get a flat top distribution classically, which meaning that you can find it anywhere, it's totally uniformly distributed. But a particle localized in the box quantum mechanically, like an electron or an atom inside of a box that's small, microscopic, it has this wave-like structure instead, right? There are points where there are points in the box that are of higher probability, i.e. the particle exists for longer or spends more time in those regions where the probability is high. And then there are actually 3 points in the curve, which are on the walls and in the middle of the box, where you'll never find the particle. 0 probability. And of course, we call these nodes, right, which is a node is where psi squared is 0, right? The points where psi squared is 0. Right, so there are defined points in the middle of the box, and as n gets bigger, there are more and more of them, where you're not going to find the particle, right? Which is completely opposite of what we would expect for a random collection of bouncing balls in our box. So this is kind of an important kind of point, right? It shows that we have very different behavior. Right, and alongside of that, right, and this is kind of a consequence of this, is that the energies are discrete, right? Which means that there are gaps between the allowed energies of the system and that they're quantized, meaning you can count them. Discrete means gaps exist and they're quantized, which means you can label them by a number, an integer. Right. And we saw that, right? The energy of these states is h squared n squared over 8 ml squared, where n is 1, 2, blah, blah, blah. Right? Right. Very different than the classical particle, which you can drop in the box at any energy you please, and it will move accordingly. Right? And also, not only that, you could drop it in and it doesn't move at all. Or you can drop a particle inside this box, a classical one, a billiard ball. You can drop it in the middle of the box with no kinetic energy, and it's happy to sit there unmoving. But what this tells us is that for a quantum mechanical particle, like an electron or an atom in this microscopic box, n has to be at least 1, can't be 0, which means that an electron in this box is always moving, regardless of how little energy it has. It always has non-zero energy. This particle always, which is a huge, right? This basically means there are no zero energy states. There is no zero temperature for this box. And in some sense, we've already, and I've kind of mentioned this before, is that the fact that there is no zero energy state for this quantum mechanical particle in this tiny microscopic box is proof that is the proof of the third degree of thermodynamics, the third law of thermodynamics, which is that temperature can never go to 0 Kelvin. It's impossible to reach 0 Kelvin, because if you pull all the heat out of your quantum mechanical, your box, all you're left with is a particle that is in the ground state of this box, which has energy equal to where n equals 1 here. There is no n equals 0 state. So you can never remove that energy. It's always there. Meaning that the system will always have some heat. If you had a collection of these little electrons in the box, it would have some heat, and therefore it would have a temperature. Right? They can never go to 0. Right? So there is no energy, there is no zero energy state. And that's going to be really important for us. This has deep consequences in chemistry. There are states that have no, there are, in some sense, a universal state for every system like this that it always has energy. You never have zero energy. And we're going to see that again this week. And of course, the last thing is, and I'll just make a note, is that we saw in this box, the walls are infinitely high. Right, we saw, right, this is how we derive those wave functions, is that psi of x goes to 0. as X goes to either 0 or L. Right, so psi disappears at the wall, right? Which means, of course, that there's no probability that the particle is embedded inside the wall or outside the wall. Okay, but what happened when we drop the walls to a finite energy? Finitely high. Psi of X only goes to 0 as X goes to infinity or minus infinity. Right, so the moment that the box has some escape, some ability to escape, there's always going to be a little bit of probability outside the walls because the wave function is only 0 at the infinite limit. Right, when I have an infinite box, I've effectively truncated my space into a finite region between 0 and L. There is no space to the particle outside the box because it can't escape. Okay, so the box is, in some sense, the space that the particle exists in an infinite box is finite, only length out. But the moment the box becomes finite, as in you can apply enough energy to the particle, allow it to escape, then you've changed the bounds of your system to negative infinity to positive infinity, and the wave function has to go to 0 at the edges, and those edges are at infinity. And what that means is that there's always going to be some non-zero probability outside of the walls. It might be vanishingly small. It may be worth neglecting if the walls are high enough, but it's always non-zero. Right, so the probability psi outside walls, it's not equal to 0. Right, there's always some probability it will escape. These three observations, keep in mind. We have this wave-like property of the system inside of the potential, inside of the box. It has quantized energy levels. And only when the box is infinite is the wave function finite. Fixed, right? The way that the walls are finite, there's some ability to kind of go beyond the walls, then it will. And it will go out to infinity or minus infinity. Okay, so let's keep those in mind. All right, so we have these three kind of simple principles. Now what I want to look at is as a different system. Now what I want to do is I want to take our particle. Right? We don't have to, you can put it in a box, that's fine. We won't have to worry about the box right now. And I want to attach it to another one. Right, so I want to have two particles that are connected to each other with some strength. Right, so let's consider this, right? We're going to have to think about what the motion of this part system is. I'm thinking about, and an example we're going to use is we're going to attach two masses to the end of the spring like this giant cylinder I have in my hand. Right, so what that means is that we're going to have two objects, two masses, two balls, two particles that we're going to attach to something that's stretchy. Okay, that's something that we can apply a force to stretch. Right, and we can define how tough or weak it is, how floppy or strong how much resistance it has to pulling it. But let's just attach two things with some glue at some distance. Right, so we're going to consider a new type of motion. Particle confined to another. Right? And we're gonna confine it again such that you can manipulate the distance between them. So we're not going to have an infinitely strong bond between them, basically, or it's fixed. Right? Where the distance between them is rigid, but in the sense that you can grab both ends and stretch it. Right? It's going to have some stretchiness to it. Right, so the way we're going to model this is we're going to take two masses, let's say atom A, right? And it's got mass M sub A. Right, and then we're going to take another mass B with mass M sub B, and we're going to attach them with a spring. Here's my slinky, if you will. Okay. And what I'm going to do is define something about the distance between them. The distance between A and B can be any value it wants to be. But but with a spring, right? Let's see, actually, this might be so long that I can't actually make this equilibrate. So let me make the spring a little shorter. But for a given spring, there is some, in some sense, if I just let it go freely, there's some like equilibrium length that it likes to sit at, right? And of course, this length is determined by the force due to gravity. Right, there's a constant force being applied from gravity straight down. That's applying a constant force on the spring and causing it to stretch. And so think about this equilibrium distance. There's a constant force being applied to stretch it, and there's some distance where this kind of, as you can see, it's oscillating up and down at the moment. But there's some average position that this length sits at. Right? It's roughly, put it down at the foot. Right, it's about 3.5 feet for this, right? Because I'm about 6 feet tall. And this is about half my height. So it's about 3.5 feet or so. Okay, so I'm going to have this equilibrium distance. I'm going to define it with a fixed value. So we always know what the length of the equilibrium length of the spring is. And I think I define this as, yeah, so let's think we have some distance between here. L, right? And so L is the length of the spring. And we're going to define L naught to be the what we call the equilibrium length at rest. Right? It's at 3.5 feet. And of course, I can do something to this spring, of course. It's not just sitting here. And of course, because I've given it some kind of jiggly force, it's oscillating up and down. But I'm free to apply an external force to it by either compressing it in this way, right? By applying a force against gravity, or I can apply a force along gravity, which is kind of hard to do because I'm not tall enough. Right? I can apply an extending force as well, right? I can apply some force, and I actually can feel some resistance where it's trying to press back, right? So as I apply an extending force, the spring itself is creating a reciprocal force that wants to return it back to the equilibrium position, right? So as I stretch it out this way, it wants to come back in, and if I compress it, it wants to go back out, right? So there's some restoring force built into the spring, right? The spring isn't just freely settable, right? It wants to come back, always come back to equilibrium. Right, so if I apply a force, let's just, again, if this is physics 101 for you guys, I apologize, but it's worth going through this one more time. So the spring will always apply a restoring force in the opposite direction of the displacement of the spring. Right, so if I stretch it where L minus L0 is greater than 0, right? So if I set my new length to be L prime, which is L0 plus L, right? There's going to be a force. The spring is going to apply a force against me stretching it to bring it back. This restoring force. So the force that the spring applies, we can kind of say is negative, right? Negative force means you want to come back together. Positive force, you want us to spread it. And vice versa, right? I can write plus or minus, right? And it's less than 0. if plus and greater than 0 if minus. Right, so what this means is that in some sense that there's this force that gets created inside the spring when I displace it. It's a function of my displacement. And so and there's always this force and it always wants to come back, right? So the force is always opposite of the displacement force, this restoring force, and it's a function of the distance. The idea is that as you stretch it more and more, the restoring force becomes greater and greater, right? If I just stretch my spring a little bit, like this, right? The amount of force that the spring has is very little, right? You can see the oscillations are very small. The oscillation of the spring after I've displaced it is fairly small amplitude because I've applied very little energy to it and therefore it's restored with very little energy. But if I stretch it really far, right, the whole thing oscillates at a much higher oscillation frequency. Now, because this is plastic, it's quite damped. As you can see, the oscillations dissipate very rapidly because this is just a plastic spring. Right, but in some sense, the restoring force is a function of the position of the spring. The bigger the spring, the more restoring force it has. So let's think about that, right? So we have two atoms A attached to B, and they're at some distance L, right? Let's say actually, yeah, some distance L. Right, and we want to calculate the force that the spring feels as a function of displacement from L naught. All right, so we'll start initially at L naught. And let's define the axis system so that this is at 0. And this is at some value L. Let's say, yeah, L, initially at L naught. So we're going to start at length equals L naught. Right, and here the force of the spring is 0. Right, because it's at equilibrium, it doesn't really feel a force one way or the other. Right, and what I'm going to assume now is that as I stretch it, the restoring force is linear in the displacement. Okay, so if I double the length of the spring, the returning force of the spring is twice as much as it would be if I were at length. So let me start over again, so it's clear. So let's say I stretch it so that I double the length to 2L naught. Okay, and so let's say I have some restoring force that the spring has at 2L naught. So double the length of the spring. Now let me triple the length of the spring. Or let's say quadruple, right? So let's say I go from 2LO to 4LO. Right, so I've doubled the length of it again. So now it's 4 times originally as long. The restoring force is twice as much as I had at 2LO. All right, so we have a linear relationship between restoring force and let's just assume that we have a linear relationship between the restoring force and the displacement of the spring. So what I could write then, we could say that the force of the spring, we'll say is, again, sorry, can't spell, is linear. If it lets me write. Oh, sorry, my program just crashed. The room's a little hot and I can feel it in my computer. My computer's overheating a bit. Lost my notes. Let's see. I should have like an auto save in here. I don't. Great. Okay. All right. Well, fuck it, I guess. We'll do it live. All right. So I have let me just redraw. We'll say initially this is at some length L naught. And we're going to say that the force of the spring, the derivative as a function of the displacement, Right, so let's think about that, right? So it's a linear force. So as I double the length, the force will only double. So that means that the derivative of the force with respect to length is just a constant, right? Force is a straight line as a function of the displacement. So this is, we'll just call this some constant K. And we have, so this is just a constant. And it's called, we always call this what's called the force constant for a spring. There's a couple different words that people often use for this constant. But in chemistry, we always call it a force constant. We'll have to think about the units and what it means, but we'll come back to that. All right, but just think, okay, we have a linear displacement. And of course, what this means is that when I integrate both sides, the force acting on the spring as a function of L minus L naught is just K L minus L naught. Right, so it's just a linear function of that. So this K is a force constant. It has some sort, it's some sort of parameter that tells you how much resistance the spring has to stretch, right? How much restoring force in newtons do you get per unit stretch? Right, so the force constant measures in some sense the stiffness of the spring. Meaning that as K gets larger, the force required to stretch goes to infinity as well. It's a function of that. Okay. And so this spring in particular, compared to say springs that you may find in your engine, for instance, the springs that open and close the valves on your engine and things like that, those are very, very stiff springs. You have to apply a lot of energy to stretch those. And when you stretch them, they snap back into place really fast because you want them to be very precise. Right? So a spring in like a car or something like that is generally very stiff material. You have to apply a lot of force to it because you only want it to open a small amount. And you don't, the last thing you want to stretch in a car, as you have exhaust valves that open and close to bring in air and fuel, and then once to open to exhaust, you want those things to open and close very precisely, and you don't want them to chatter. Something, if you're a car nerd, you've probably heard of valve chatter. If your valves are in the line properly, they clap like this against the openings in your pistons, and or the intake ports rather, or the exhaust ports. And so you can kind of think of this chatter. This is a very, very loose spring. This would be a terrible spring for combustion, because if you want to say this is your intake spring and you want to open the valve to let some air in, you apply a little force and it flies up. And then when you let go and you're ready to close it because you're going to open the exhaust valve to let the exhaust out, this thing is just like this, right? You can see that, right? It's oscillating rapidly. And that's a function of the stiffness. If you have a very loose spring, and this is a part of relaxation, which we haven't discussed yet, about the slowing down of these springs, but the stiffer the spring is, the faster it's going to equilibrate back to the original position. And so if you have a very loose spring and you stretch it, it's just going to bounce like this forever and ever. It doesn't dissipate the energy very rapidly. And so you get valve chatter, right? The valve kind of goes like this. If you have a Subaru, an old Subaru, they love to chatter a lot, especially after a fresh oil change. Very common in them because their valves are sideways. So on a Subaru engine, they go like this. Instead of a normal engine, they go up and down where you have gravity assist. In the Subaru engine, everything's sideways, so they chatter because gravity is acting in the opposite direction. And so you typically have very strong, really stiff springs, so that first of all, you apply a very fixed amount of energy and they open a very small amount because you just need to open them enough to let air in or fuel in. And then when you close them, they snap back into place really quickly. There's a lot of force, returning force to snap it back into place. Okay, so that's again a very classical approach to springs. Why is that relevant to chemistry? Well, the way that I want to, I think maybe it should be obvious why I've modeled this the way I have is, again, think A and B are atoms and we've attached a bond between them. And so we're going to tackle bonds in the exact same way. Right? That the bond between a molecule in some sense is a spring of some stiffness. And of course, the stronger the bond, the more stiff the bond typically is. We'll see that that's not always true, but we'll think about that a little bit, about strength versus stiffness. But you could say, okay, well, a strong bond, like say a carbon-hydrogen bond, for instance, or a carbon-carbon double bond, something that's very stiff, doesn't move a lot, has a very high spring constant. Right? And they're very strong springs. Whereas something like a hydrogen attached to an oxygen, like an OH group or a carboxylic acid, where the atom is somewhat labile, right? And where it can leave because of acid-base catalysis and stuff like that. Yeah, that can be that's often models a very floppy spring. That atom can kind of just fall off. It's not really strongly attached to the atom. And we model those with kind of more, this kind of spring, right? Not so stiff, kind of floppy. And we have different terms for that, as we'll see. All right, so we're going to kind of correlate this to bonds, right? That's kind of the goal that I want ultimately is to think about this in terms of the strength of bonds, right? And we're going to have to think a little bit about bonds very carefully because I've not mentioned anything about electrons. Because you guys know, if you have a covalent bond, they're sharing electrons between, right? There's electrons in some sense being shared between A and B. How do these electrons come into play? As far as I've looked at this, these are two balls. In fact, these are just two nuclei, right? Because the majority of mass in an atom is the nuclei, like the protons and the neutrons. Proton is 1,000 times bigger than an electron. So most of A and B are just nuclei, right? So this is nuclear motion we're thinking about, not electronic motion. And then you might have to think, well, if we're moving the nuclei, aren't we also moving the electrons? Right? So we'll have to think about that a little bit. It's a little subtle, but we'll have a solution for that. And what we'll find is that actually this works extremely well for modeling bonds in this regard. And then we'll have to think a little bit more carefully about the electrons afterwards. All right, so just kind of think of these as two nuclei. Say if this is HCl, A is H and B is chlorine, right? And they're mostly just nuclei, and you've attached them with some bond that in some sense is some average sharing of the electrons between the atoms, right? Think of the bond as just kind of an averaging of the electrons between, right? And we were going to model that as a spring. Well, so we have this forces, this restoring force is a linear function of the length. Now, when we're going to start working in quantum mechanics, remember we want to solve, we're not really concerned about forces, right? We're concerned about energies, right? Ultimately, we're going to write down some operators for energies and find wave functions for this system. And so we need to think about the energy that's stored inside the spring as a function of the displacement. And here's a nice formula that's really useful to never forget. Maybe it is useful to forget. I'm not sure. I always remember it. But one of the classic kind of comes from Newton's laws is that you can always write the force acting on something as minus the derivative of the potential energy with respect to position. Right? So this V here is the potential energy of the system. Okay, so this force right here, this linear function of L, is equal to the derivative of the potential energy of the spring times -1. Right, and so all we have to do, right, to calculate this is we just calculate the potential energy is we need to integrate both sides. Right, if I multiply both sides by dx, I get f dx is equal to minus dv. Right, and if I integrate both sides, right, if I take the integral of the force with respect to position, I get the potential out, right? Because this just integrates the V, negative V. So plugging this in, I have that the integral of K L minus L naught dl, I'm just replacing X with L here, is equal to minus, well, this is just the integral of V, dV, which is just V, so I'll just write minus V of X here. It's the integral of that. And so I just have to integrate this constant function, or sorry, not kind of linear function with respect to its parameter, which just gives me the parameter squared, right? Integral of the line is L x squared. And so already I've solved a very useful equation that says that the potential energy of the spring is equal to minus 1/2 K L minus L naught squared. So now we've already come up with, we've already defined in some sense, this is everything we need to know in some sense about the energy of this spring. We have some particles that have some kinetic energy. We'll have to think about that because they're moving. But as a function of the position of those two particles with kinetic energy, depending on which way they're moving, we have an additional potential energy, which is negative, as it should be. Right? If you have two objects with kinetic energy that are moving this way on your spring, stretching the spring, the potential energy wants to drive the system in the opposite direction. So positive kinetic energy means negative potential. Right? So that's why we have that negative sign here. And the idea is that when we have kinetic energy, that's going to drive our particles either apart or together, depending on which way they're moving relative to each other. And the spring has its own potential energy that gets created based on how much energy, kinetic energy, those two particles transfer into the spring, whether they're pulling against it to stretch it or they're pushing against it to compress it. You've taken some of that kinetic energy and converted it into potential energy. Right? So we're going to have a balance now of kinetic and potential energy in our spring. Right? This is a new feature, right? And remember in the particle in the box, our potential was a constant value. It was 0 inside the box and infinite elsewhere. It had no position information. Here we have a system that's moving with potential energy. It's got kinetic energy, but it also has a potential energy that's a function of the position. Right, so it depends, if you think about this, a spring being in a box where you could stretch it to the ends of the box or the middle of the box. This means that now you have each value of that stretch has a potential energy. It's not constant anymore, it varies now. So now you have this competition, if you will, between kinetic energy and potential energy. So when we think about the energy states of this system, they're going to experience as a function of the position of the atom in the box, if you will have a balance of kinetic and potential energy. Right? It's not just kinetic energy. There's some potential as well. Right, and we can, and it's really easy to kind of see this. If we just do a little bit of intro physics on this really quickly. Well, let's come back to that actually. Let's do a bit more physics on this. All right, so let's just solve. Now that we have a potential and a force, we can solve Newton's laws. Because remember, we have Newton's second law, which means force is equal to mass times acceleration. Right? F equals ma. We have a force, we have a potential, we can solve for the time dependence of the system, how the atoms move as a function of time by using F equals ma. So let's do that. So Newton's second law. Says F is equal to m times the acceleration. Of course, force has a displacement. It's a vector. Of course, this is in one dimension, so we don't really care about vectors. Right, and remember what the acceleration is defined as. Acceleration is defined as the second derivative of position with respect to time. So this is equal to the mass of the object times the second derivative of length with respect to time squared. And this is going to be equal to the force, which is minus K L minus L naught. All right, so we have a couple things. So we have a very interesting equation here. We says whatever L, if we think of L as a function of time, right, which is just the position of the object, this is the second derivative of the position with respect to time is equal to the position. All right, so this is actually an equation we can solve, but there's a couple of things we haven't really quite defined here yet. So we have this L minus L naught. This tells us something about the position of the system and the spring from displacement. But we also have this mass here. And how are we going to define the mass for this system? Right, because we have two masses. Right, so do we sum the masses? Or do we do something special with them? All right, well, what I'm going to do instead, right, because what we actually have are two masses that can move independently of each other. Right, you can kind of think of if you have this spring here, initially at this position, this, get a little shorter so it's nice and stiff, right? I can move this one separately from this one, right? I can move this one up, and move this one up, move this one forward, right? Each one can move independently of each other. All right, so in fact, if I want to solve this equation, right, if you think about it in terms of like physics 101, I'm going to have to think about the relative position between the two atoms, right? Because I have two atoms, but they're always connected by a line, right? So what I can do instead is instead of thinking about each atom moving separately, which is a real pain in the butt, right? Because each atom ideally has 3 coordinates, x, y, and z, so it's a 6-coordinate problem. We can always use the fact that the two are on a line like this. And if we move things to the center of mass frame, we'll talk a little bit about that if you don't remember, then we can talk about it in terms of relative motion. Right? So in the sense that we can take this motion, right, let's say stretching motion, and instead transform it to a system where I fixed one of the positions of the spring, so like I'm holding this in place, and I move the spring in such a way that I've changed the mass on this so that this motion looks exactly the same as this. Right, so what I'm doing is basically instead of having, right, if you think about it, your camera perspective of the two atoms right now, as they stretch like this, your camera is from the laboratory point of view, right? You're sitting where I am, and you're seeing these two atoms move independently of each other like this, right? So you're tracking both. But remember, Einstein says, and Newton says that, you know, the physics are the same regardless of the point of view. So what we can do instead is set our camera on one of these masses, right? So let's say I stand on this one over here, right? So from my point of view, this atom is not moving because I'm standing on it. And what do I see? I see this one moving. Stationary. It's exactly the same motion. It's still this from you guys' point of view. But if we put the classroom on this one, this looks like it's stationary and this is moving against us. Right? So let's look at it from that perspective, because from this perspective, our point, this atom right here that we're standing on is fixed in space. It's not moving. It's just standing, and we're watching this one move relative to us. And so we've reduced a 6-coordinate problem to a 3-coordinate problem. Right? Instead of it both masses, it's just one moving relative to another. Right, so let's move to that position, right? So now what we can think about is a spring hooked up to a wall that's unmoving, and we have some sort of equivalent mass stretching the spring and moving independently. So it's just one mass moving against a wall. Right, and it's not too hard to calculate this. This is just a classic 2-body problem from intro physics. But the idea is that we take this system, MA, MB at some distance L. Right? And each one of these atoms, if you will, the position of atom B is a coordinate of XB, YB, and ZB. And this atom is moving in some direction A, which is a function of its coordinates. Right? We're going to transform this problem by shifting to the center of mass. Where now what we have is a fixed wall in place with a spring attached to it, right, of the same length. Right, but what I'm going to do now is attach a different mass to it of a different shape, which we call the reduced mass. We'll call this mu, where mu, the mass of mu, is MA times MB over MA plus MB. This is what we call the reduced mass. I won't go into the details of how we convert between these two. I assume you saw it in physics 101. Physics. If not, I'll put some, just send me an email and I'll send you some resources if you're not really clear about how we're doing this transformation. But this is perfectly valid. Right? And this allows me now to use this equation directly, because now I have only one coordinate, right? Just the length. Just the length of the spring. I don't have to worry about where B is and where A is relative to each other. Instead, what I have now is a mass whose mass is like a weighted average, if you will, a weighted average of the masses, the two masses on the spring, the reduced mass, and it's just moving independently next to a fixed wall. Right? So I'm only doing this just to simplify the math. It's not to say that this is how an atom looks like, or a bond looks like, that you have a rigid body and you're moving a ball against it, but rather that I can always take this problem here and convert it into this. And now it's just a function of one atom, right? This one magical imaginary atom with a special mass, mu. So what I can do now is relabel this equation. Right, so now I have mu times the second derivative of position with respect to time is equal to minus K L minus L naught. Okay, and I'm just going to simplify this a little bit. So let's let X naught equals L minus L naught. Sorry, let's let X equals L minus L naught. And so I can rewrite this very easily as mu d squared x dt squared is equal to minus kx. Okay. So let me just rearrange and simplify this just a bit. What it says is that if I take the derivative of whatever my position is with respect to time, second derivative, I get the position out times this force constant divided by this reduced mass. Right? So X is again the position of this test atom, this imaginary atom, at the center of mass, the center of the reduced mass as a function of time, right? So X here is a function of time. It's some function that explains how this particle moves at some distance as a function of time. And what this is saying is that when I take the second derivative of this function with respect to time, I get the function back times some numbers. All right, well, we've seen this behavior before, this kind of equation. It's called, this is a second order differential equation, as they call it in math. But we've seen one similar to this, remember when we were solving the particle in the box, we solved in a similar equation, which said that the derivative of psi with respect to this, the second derivative of psi with respect to position is equal to some number k, sorry, let me make k, times psi. Right, so when we solve this problem, we said, hey, what are the functions psi that are continuous and satisfy our properties that satisfy the property that when you take two derivatives with respect to position, you get the same function out times a number. And of course, we saw very quickly, right, that psi can be either sine of x or cosine of x. Right, that's how we got those out, right? And so same thing here, right? We have the same kind of formula, except instead of x, we're using t, and our function's not the psi, it's the position with respect to time, and it satisfies the same equation that we had before. Right, so we already know what the solution of this is, right? We know that it's some sort of sines and cosines, if you will. Right? And what you find is that x of t here can be written as a, let me actually erase this. Let me write this on a bigger, let me go to the next page so I have some space. We're going to talk about this solution. This is particle in box. Right, so let's just go ahead and bring this over here. Right, and the general solutions for this are some number C1 times cosine. Well, let's say sine. It doesn't really matter which one we use, I guess. Sine of omega t plus C2. Cosine omega t, where omega is equal to the square root of k over mu. So what this is saying is that when I stretch my system, if it's at equilibrium, it shouldn't oscillate at all. Of course, it's oscillating a little bit because it's slightly stretched. Right, but it says that if I stretch it away from equilibrium, that the position, if you will, of the tip of this spring will move as a sine wave, and that's exactly what we see. Right, falling, right, up, down, up, down, up, down. Right, it's oscillatory. Right, and depending on where we start, C1 or C2, depending on this boundary, the starting conditions of our spring, C1 might be 0 or C2 might be 0. Okay, it just depends. Right, but it can be a mix of both. And the frequency at which it oscillates is a function of how stiff the bond is divided by how heavy things are. Right? So what this is saying that is that when you stretch this, right, the amplitude of the oscillation, if you will, right, which is how far it goes down and comes back up, right, the vertical displacement of the stretch of the oscillation is a function of how hard I stretch it. Right, but if you notice, there's a frequency at which this system oscillates. It's a little hard to see, but that frequency, in some sense, doesn't change whether or not I'm at equilibrium. It's a little hard to see that. Or if I stretch it at the same time, the frequency at which it bounces back and forth is roughly the same. And the reason why it's roughly the same is because the frequency is determined by the stiffness of the spring, which as far as we know is a constant of the spring. It just tells you how floppy the spring is, divided by the mass that's attached to it. Now, in my case, I don't really have a mass here. M1 is equal to M2, so mu is 1. Because I don't really have anything attached to it. Maybe if I have something attached to it. Maybe I'll watch. Let's try this. Right, so what'll happen is that if I attach a mass to this, attach it to a couple more, is that the oscillation frequency should decrease. Because K is fixed for the spring, it's just Slinky has defined this plastic to have some sort of stretchiness to it. But the mass on either end is the same, so mu is 1. All right, so now what I'm going to do is attach my watch to the end of it, which is add some mass to the bottom. And what should happen is that the spring should oscillate more slowly. Might not be enough mass, we'll see, than it did before. All right, so let's get a sense of how long that takes. It's roughly 1 second an oscillation or so. 1 second a period. Let's just say it's roughly 1 second a period. And then I'll take my mass off. A little faster. Would you guys agree with that? Maybe a little bit. Maybe it's not the most obvious thing in the world. I'll come with maybe I need to get like a lead weight or something. All right, so what that means is that the amplitude of the wave, if you will, the values of C1, C2 are determined by the initial stretching, by basically the initial conditions, whether stretched or not. But the frequency of oscillation has nothing to do with how you stretch the system. It only has to do with the mass attached to it and how stiff the spring is. It's unique to the system. Right? It's unique to the combinations of mass and spring. Independent of energy. Right? It doesn't matter how much energy I put into that spring, it oscillates at the same frequency regardless, as long as I have the same mass on. Okay. So now let's think a little bit about how energy is flowing through this system. Again, I'm just kind of going through the basics so we have a really clear sense of how we're going to tackle this quantum mechanically. And we're going to do exactly the same way. I'm going to take this system just like I did other systems. I've got a ball bouncing between two walls. Here, what I'm going to do, and then I solve for the wave functions that satisfy the energy equation, right? That when I plug in the energy, measure the energy, I get the same wave function back times the energy. I'm going to do the same thing here. But the important thing is that the difference between this and a particle box is now I have a non-zero potential. Potential is a function, it's not constant, it's a function of position. And so let's just kind of recall how this spring system works in terms of energy. Go ahead and go to the next page, right? So let's do some energy analysis. The total energy is equal to the kinetic energy plus the potential energy. And of course, the kinetic energy is 1/2 mu v squared, right? Which is the velocity of that mass at a given point, plus 1/2 kx squared. Remember that x here is equal to L minus L naught. Okay, another way I can write this is 1/2 mu, and this is the derivative of x of t with respect to time squared plus 1/2 k x of t squared. Right, so the energy in some sense, right, the kinetic energy as this thing stretches, it's time dependent. The position of the mass on this imaginary mass and the position of the spring as it oscillates is time dependent. And what that means is that the kinetic energy and the potential energy are also time dependent as well. Right, so I can just plug in my value for x of t here. So let's just take one, right? So let's let x of t be a cosine k over mu t, where a is just some number, some amplitude, just a number. It's how hard we stretch it, if you will. And so this comes out to 1/2 mu cosine squared, sorry, a squared cosine squared k over mu t plus 1/2 k cosine squared k over mu t. Sorry. Let me erase. I apologize, guys. I forgot to clean something up here. I forgot to take the derivative of it. It's the derivative of a cosine k over mu t dt all squared. Right, I take the square of the derivative. I apologize. Right, that's easy enough to do, right? The derivative of cosine is sine, negative sine. So we can just evaluate that immediately. The negative goes away because it's all squared. Right, so we're going to get a minus sine omega over t. And then we square that, so it's going to be a squared plus whatever's in here squared sine squared omega t. Yeah, go ahead.
Like the a squared, why would that come outside?
It's I forgot to erase it. Yeah, sorry, thank you. Thank you. So this is where it comes out. So let me just evaluate this. So we get 1/2 mu a squared. And then from the chain rule, we have to take a derivative of the interior. So we're going to get a factor of k over mu square root, and it gets squared. So we have a factor of k over mu that comes out. And then we're left with sine squared k over mu t plus 1/2 k cosine squared of k over mu t. I could do some simplifications here. Right, if you see the mu's, the mu's cancel out here. And I'm left with 1/2. Sorry, I missed a factor of a squared here. There's an a squared in there. A squared k sine squared k over mu t plus cosine squared k over mu t. And what's sine squared plus cosine squared? 1. So this is left to 1/2 a squared k. Right? So what this means is that the total energy, right, this is the total energy of the system, and it's just a number. Total energy is just a number. And is therefore conserved. Right, which is exactly what we want, right? We always want our energy to be conserved. Right, so we always want to define something so that the energy is not changing in time. Kind of a useful thing to have, right? So that every spring at every time acts exactly the same way. So the total energy of the spring has to do with our displacement, right? That's how hard we stretch it. A squared is a function of how hard we stretch the spring, right? Which is the oscillation amplitude, the magnitude of displacement from equilibrium. And then it's times the stiffness of the spring, right? The stiffer the spring, the harder we have to pull it to displace it to some distance. So the amount of energy has to be proportional to K, because if it were a stiff spring, twice as stiff, it's going to take twice as much energy to stretch it. All right, so if we look at how the energy flows in this system, then if we make a little plot here along X of the potential energy, which is just, remember, potential energy is just a parabola. So it looks like this. This is my potential energy curve, just a nice smooth parabola. I'm just gonna go. Great, almost done. Right, and the idea is that right, each one of these positions correspond to a different stretch or different displacement. And let's think a little bit, right? And what it says is that every point along this curve, the energy is constant. Right, so no matter however much potential energy I have, I lose that in kinetic energy. Right, so if I'm down here at the bottom, well, let's say I initially stretch a spring. Okay, well, let's stretch the spring some distance. Okay, let's start from some initial time where I've stretched it. Right, so here we'll call this our t equals 0 point. Right, I've stretched it this much. Delta X. Right, and the total energy at that point, has to be 1/2 a squared k. Right, k is a fixed number, so a in some sense has to be equal to has to be proportional to this delta x. Right? Because the total energy here is only a function of delta x. The potential energy is a function of delta x. The total energy is just a function of a squared and a constant. K doesn't change. It's fixed to the string. So A must be a function of delta x as well. Okay, so A tells you again how much you've displaced the spring when you stretch it. Right, and so again, what I've done effectively is I've taken my spring. Up there, a few turns, right? And I stretch it like this. That's at t equals 0, right? There's a bunch of potential energy in here, right? I can feel it pressing against me. I can feel it wanting to stretch back. Right? But there's no kinetic energy in this system, right? No kinetic energy. Because I'm holding it in place at t equals 0. Right. So here, right, in some sense, this is the energy that I've placed into the spring. Right, this is E. Right, so this is the total energy of the spring right there, right? How much I've stretched it. Right, so at this point, it's all potential energy. Right, V is max because it's non-zero. So V is equal to E here, and therefore T is equal to 0. There's no motion. Right, so now I let the spring go and it compresses, right? Just to remind you, not that you should not be gaslit about the spring at this point, but just in case. Stretched it, right? And it immediately starts to return. It goes back to the other side, right? Before it comes back down, it compresses and then expands again, right? So what happens now is the potential energy is released from the spring and converted into kinetic energy. Right? And the spring is going to pass the equilibrium position, which is at x equals 0. Right? X equals 0. Here, the potential is 0, and that means that the kinetic energy is maximum, and there's total kinetic energy, right? So I've stored a bunch of energy into the spring, I've let it go, and it's as the spring compresses, it converts that potential energy into kinetic energy. Right? And then the opposite happens as it goes up the spring, right? And as it goes back up, as it compresses again, it's going to fly back. And if the spring doesn't have any energy loss, it's going to end up at the same point on the opposite side of the potential. We'll call this 1/2 the period. Halfway through the period. And here again, the potential is the energy and the kinetic energy is 0. And then, of course, the system goes back and oscillates again, right? It's a sinusoidal. Right, so what this is saying is that the motion of the system, right? So unlike the particle in the box, all the energy is kinetic energy. It's always moving. There's no potential because there's no preference for the particle to be in one point in the box or another. The only preference that appears is probabilistic, and it comes from the wave function. But from the point of view of the box, it doesn't have any bias one way or the other. But here we have an obvious bias. Right? This system's kinetic energy is inversely proportional to its potential energy. So as you build up potential energy in the system, you lose kinetic energy. And as you build up kinetic energy, you lose potential energy. Right? So this is a system where there's always potential energy and there's always kinetic energy. There's always a balance between them. So this is a system. I think this is going to be, so the bond, chemical bond, is a system that experiences both kinetic and potential. And I'm about to crash, I think. Yep, there it goes. It crashes. Fantastic. All right. Right. So let's hold that on to that thought. Okay. So we now have a kinetic energy and a potential energy. So when we go down now, our next step, which will be on what's our next day? Wednesday, is we're going to take that energy, right? Kinetic plus potential. Now we're going to have a new energy operator when we construct our box to measure energy. And we want to define the values of the wave functions that satisfy the constant energy states. We're now going to have two terms. We're going to have the kinetic energy and the potential energy. And so now we have a slightly different scenario. We're going to have a different set of wave functions because now we have this potential energy that's turned on. And it's going to give us different energy levels and different wave functions and different properties altogether. Okay, so we'll tackle the quantum mechanical part of this next class. Hopefully my computer won't crash next time. And I'll make sure to post some notes about this as well for you guys today. Thanks, guys. Have a good one.
I don't know, but it's just not gonna write it easy. I'm not gonna hold you.